Well, hello. Today we're going to talk about Depth Map Automatic Generator 5, aka DMAG5. So the advantage of using DMAG5 over DMAG2 is that it's faster, and the running time doesn't depend on the radius. That's the main thing. But DMAG2 will always be slightly better than DMAG5. So, it's a trade-off. DMAG5 is much faster than DMAG2, especially for larger radiuses or radii. So that's why DMAG5 is used the most. But DMAG2, should generate better depth maps in general, because DMAG5 is an approximation of the bilateral filter, and DMAG2 is not. It's actually a full implementation of the bilateral filter, and that's why it's slow. Okay, so the reason I'm doing this video is because DMAG5 is now on GitHub, and I'll put a link in the description. But yeah, that's why I'm making this video, so that you know that the code is there. It's in C. Okay, let me see. Of course, I will give a link to this blog post I made about DMAG5, which is right here. Okay, so DMAG5 is an implementation of fast cost volume filtering for visual correspondence and beyond by Rhemann and company. So I discussed that thing in several other blog posts. So here's one, and there's another one here. But first, I think I'm going to go through this thing just to make sure I don't forget anything. Yeah, I just want to go over the parameters that control DMAG5's behavior. So those parameters, they are in the DMAG5_input.txt file. That's the input file. So you have the minimum disparity, maximum disparity. It's all explained. So the window radius is the guided filter size. So the nice thing about DMAG5 is that the running time doesn't depend on this radius. It could be small, it could be large, it doesn't make any difference. Alpha, yeah, okay, so that balances the color matching cost and the gradient matching cost. So the default is 0.9, so you give more importance to the gradient matching cost, which makes sense because if you have different illumination between the left and right images, the color matching cost is not going to be very useful. So that's why you have a gradient matching cost. And the gradient matching cost is, it doesn't really matter if you have illumination differences between the two images. So default 0.9, it works well, so I keep it that way. Truncation value for the color. So I usually use 30 or 20, and there's a truncation value for the gradient. So here I use 10, but you can use lower stuff. Some people use 2. So it's just to reduce the effects of occluded pixels between the left and the right images. If you want, you don't have to. You can put some large values and it's not going to have any effect. Epsilon controls the smoothness of the depth map. So here I'm saying that as epsilon is lower, then it can become negative. The depth map gets smoother. Okay. And then you have stuff that's also in DMAG2, same thing, disparity tolerance. So when you compute the left and right, if the disparities don't match, you mark the pixel as having unknown disparity and use something else to compute the disparity. That's what it's all about. So those disparity tolerance, window radius, sigma space, sigma color, that's all about occlusion. So it doesn't really matter that much. And then you have the downsampling factor. So if you have very large images, use downsampling factor 2, 3, 4. So if you use downsampling factor 2, you should get a speed up of 2 by 2 equal 4. If you use downsampling factor 3, 3 by 3, 9. So a speed up of 9. Okay, and then I give an example. Okay, so now we can go into this one first. Okay, so I'm discussing a little bit. No, it's this one. So fast cost, volume filtering. Here I'm discussing the what's in that paper. Okay, so you can read this, but let me go over the how it works. So this is what's actually in DMAG5. So for each disparity D, so D is between the minimum disparity and the maximum disparity. So for each disparity D, you're gonna it's called the cost volume. So for each disparity D, there is a slice of that cost volume. So it's like a three-dimensional volume, and for each disparity you are computing a slice of it, and the size of that slice is the size of the images, the left image, right image, is that size. So for each disparity D and for each pixel in the left image, you compute the raw matching cost. It's called raw because you only look at the pixel itself, and the corresponding pixel on the right image, the ones that's shifted by the disparity D. So here P bar D, so P is a pixel on the left image, P bar D is the corresponding pixel on the right image, shifted by the disparity D, and you compute, here is I'm looking at an RGB image, so that's why you have a sum over the 3 channels. So IC of P is the intensity of the channel at pixel P, and you minus, and this is on the right. So this is the left and this is the right. So you're just looking at the intensity of the pixel. That's why it's called raw. There's no averaging, no nothing. And here so the truncation shows up here. So you take the minimum of the two. Okay, truncated absolute diff. So this step here basically creates that slice of the cost volume, but it's not smooth. It's not smooth, so it's going to be very noisy. So then you smooth the raw matching cost image using a filter. So in DMAG2 it would be a joint bilateral filter, but in DMAG5 it's a what's called the guided filter. Okay, and here, I mean, we can ignore this thing. So you do for each disparity D, so you compute the raw matching cost, and then you smooth that raw matching cost, and then at the end, for each pixel, you take the disparity that has the lowest cost. So that's how you get the disparity for each pixel. Yeah, that's what it says here. So for each pixel in the left image, the disparity that you're going to pick for the depth map corresponds to the lowest smoothed raw matching cost. Gives you the best D. I agree with that. I'm not gonna go through, but it's pretty well explained actually. Also, there's a difference in the way it's implemented. In DMAG2, you are considering each pixel in turn, and you consider that window or block around that pixel, and then you make that window or block slide on the right image. Okay, and you compute like a weighted average matching cost, and you pick the lowest one. Here in DMAG5 is different because you are computing that cost volume, and you are, for each disparity, you are so computing one slice, and then you smooth that slice. Okay, so it's a bit different in terms of how it's done, but it's the same thing. It's basically the same thing. So if you're interested in this, I suggest you read this post because it's relatively well explained. Okay, so now we have to look at the guided image filter. Okay, so here it's a bunch of images. It's not the nicest way to look at it, so let me see. At the end I give a link. Okay, for convenience, I have compiled all the images in this post into a PDF file, and I downloaded that file, and it should be here. Okay, it's easier to see. Okay, so at the beginning of that document, I talk about image filtering in general. So here you can see like a pixel eye. There's you're considering a window or a block around that pixel. It's very similar to like convolution. Pixel J is one of the pixels in that window, and here W would be the weight, etc., etc. I'm not gonna look into this, but here you can see the bilateral filter. But I want to focus on that guided filter. Okay, so let's focus on this. Okay, so given a window omega k centered at pixel k, we assume that. So Q is basically your target image, your the resulting image. So AK is just a it's an unknown. It's an unknown, so it's like a double. AK. So K again is your pixel of reference. K is the pixel of reference. I. So I is your so it's the guidance image. So it's basically your left image, the RGB image. But here it's supposed to be gray. I'm considering it grayscale to make it simpler. And BK is another unknown. And this should hold for any eye inside that window centered at pixel K. Okay, so K is is for the reference pixel, and I is for the pixel in that window centered at pixel K. So basically what we are trying to do is get a linear transform of I, the guidance image, the left image basically, within that window. And as I said, the unknowns are AK and BK. And okay, so if there is an edge in I, there will be an edge in Q, obviously. Because if you take the gradient, okay, so if you have a large change in this gradient, you're going to have a large change in here as well. So that all that that means that it's edge aware. Okay, so it's not gonna smooth across boundaries, if you will. It's not gonna smooth across edges where there's a change of color across the edge. So, okay, so we want to find AKBK such that the difference between Q and P is minimal. So Q, we know that it's a target, and P is the input. So in the case of DMAG5, P is basically that slice of the cost volume, that raw matching cost. So we want to smooth that. So P is the input, Q is the output. Okay, so now, yeah, if you look at this, the sum, so this is the sum over the window centered at pixel K. So this is the expression. AK AI plus BK minus PI square. So let's forget about the epsilon AK for now. So what you want is that when you look at that window or the block centered at K, so if you sum over the whole window, you want the output to be as close as possible to the input. So this is why you want to minimize that sum. So the sum, it's very common to do it that way. You always do like a sum of your output minus your input, and you square it. It's like Euclidean distance. So you want to minimize that distance so that your smoothed output is still close to your input. Okay, otherwise you get complete distortion. You don't actually smooth. Okay. You also have to, you want to prevent AK to become very large. So that's why you have that epsilon AK square term here. This is to prevent AK from becoming large. So that's why you don't minimize just this term, you have to minimize that, all those two terms. So to minimize E, you can solve the Euler equation, which is the gradient of E equals 0. So gradient of E is the derivative of E with respect to AK, and the derivative of E with respect to BK must be both equal to 0. That gives you the minimum. So once you have those two, you can easily find the value for AK and the value for BK. Okay, so it's a bit math intense, but I mean, you get a formula for AK. Okay, so this one is the guidance image, so basically the RGB left image. PI is your input, so this is your raw matching cost over the whole, that's the slice thing I talk about. So it's one slice of the cost volume. So the I represents a pixel in that window, the block window centered at pixel K, minus mu K, PK. Bar means it's the, what's PK bar? Hold on. What's PK bar? Okay. PK bar is the mean of P in omega K. So it's the mean. Okay, and mu K is the mean of I in omega K. Okay, so both are means, but not of the same thing. Okay, so the mu K is the mean of the guidance image, and the PK bar is the mean of the input image. And the sigma Sigma k is the variance of I in omega k. And you have the epsilon. Okay. Where is bk? Oh, bk is here, sorry. So bk was computed earlier. So bk equals bk bar minus ak mu k. Okay, so once you get the ak, you get the bk. So ak and bk are computed for each pixel k. Okay, so here there's a bit of a complication. Yeah, because a pixel I is involved in all the windows omega k that contain I. Yeah, 3 by 3 windows. Yeah, I'm not gonna go in the detail of this, but basically it means that you have to take the average of the AKs and the BKs. Yeah. So the output, so 1 over, so this is the number of pixels in the window or the block, and here I'm summing over all the pixels in the window or block. Yeah. So you get an AI bar, which is the average AK over omega I. And you have a BI bar, which is the average BK over omega I. Okay, so this is the final equation. So QI equal AI bar II plus BI bar. Okay. So QI can be very efficiently obtained using a box filter. Yeah, you have to use a box filter, because box filters are very, very efficient. Okay. And here I'm adding something. We really want to have QI, so that's your output in the following filtering form. QI equals sigma over J. So again, so this is the weight IJ PJ. Yeah, so yeah. This is just so that you can compare the weights between this guided filter and bilateral filter. That way you can visualize the weights, and you can make sense of what this stuff is doing. Otherwise it's kind of hard to understand what's going on. So here I have a lot of equations, but I'm not gonna go through that stuff. It's pretty intense. Okay, and then I also have something about if you have a color guidance image, which is the usual case, then it adds a little bit of complication because you have 3 channels. But it's the same idea. Yeah, it's the same idea. Yeah. I mean, you'll see it in the code if you want to look at it. And then here I give the kernel weights. So this way of thinking, using kernel weights, so if you want, you could actually implement it like DMAG5. Instead of doing that cost volume and the slices, you could just do it like DMAG5 by computing the kernel weights. You could do it that way. Okay, and here I'm talking about the box filter. How you compute it so that it's extremely fast. Okay. Okay, I think I'm gonna stop here. Let me go back to the blog post. Okay, so we are back to that DMAG5 blog post. Of course, so you can get the code on GitHub, and you can also get the execs on that 3D software page. Okay, just search for DMAG5, and you can also use SPM, which has DMAG5 coupled with DMAG9B. Okay, so I'm gonna stop here. If you like this kind of content, please like, comment, subscribe, and I will make more. Bye.